Welcome! In this video, we'll examine how the eye functions to help us see clear, vibrant images under a broad range of environmental conditions. First, let's consider how the eye focuses light to help us see images that are clear. Visual acuity is a measure of a person's ability to resolve fine details. In other words, it measures our ability to see clearly. Visual acuity is often measured with a Snellen chart. Snellen charts measure our ability to recognize letters of various sizes, typically from a distance of 20 feet. Visual acuity is expressed as a fraction. For instance, if you have 20/20 vision, your acuity is normal. That means the smallest letters you recognize at 20 feet are the same as the smallest letters a normal person recognizes at 20 feet. Young people often have better than normal acuity. For instance, if you have 20/10 vision, you recognize letters at 20 feet that a normal person would recognize only if they were closer to the chart at 10 feet. Older people tend to have worse than normal acuity. For instance, 20/40 vision means the smallest letters you recognize at 20 feet are the same as those recognized by a normal person farther away at 40 feet. This is how a Snellen chart might appear to someone with low visual acuity. In fact, with my glasses off, this is similar to what a Snellen chart looks like to me. For the eye to resolve fine details, light rays must be properly focused on the retina. Let's imagine we are outdoors looking at a tree that is far away. We see objects when light is reflected off those objects and enters our eyes. Incoming light first passes through the cornea, the clear bulge at the front of the eye. The cornea bends incoming light rays to help focus the image. The lens further changes the direction of the light rays to improve the focus. The focused light then strikes the retina, which is the inside surface of the back of the eyeball. When light strikes the retina, it triggers activity in photoreceptors called rods and cones. Nerve impulses are then sent to the brain to be interpreted as visual images. When we see far-off objects, only those light rays that are traveling nearly parallel to each other enter our eyes. In contrast, when we look at nearby objects, such as a newspaper, the light rays that enter our eyes are traveling in many different directions. To focus light reflected from near and far objects, the lens changes shape to accommodate for the divergence of light rays. When focusing on objects that are more than about 20 feet away, the lens is in a flattened out shape. When objects are closer than 20 feet, the lens becomes thicker to bend the light rays more. The lens changes shape when acted on by the muscles of the ciliary body. The process of focusing on nearby objects is called accommodation. Young people tend to have good near vision because the youthful lens is flexible and accommodates easily. As we age, near vision deteriorates because the lens loses much of its elasticity and fails to accommodate. This condition is called presbyopia. Presbyopia causes older people to hold reading material at arm's length, and it may cause us to need reading glasses as we age. Remember that the lens accommodates for close vision when acted on by muscles in the ciliary body. Eye strain can occur when those muscles become tired during lengthy periods of close focusing. Let's examine some common vision problems that are not caused by occupational hazards. Some vision problems are related to seeing clearly at various distances. A young person with normal vision has good acuity for both near and far objects. A vision defect called nearsightedness or myopia occurs when the eyeball is longer than normal. In a nearsighted eyeball, light rays from far objects are focused in front of the retina instead of on the retina's surface. This causes faraway objects to be blurry or out of focus. Nearsightedness does not impair close vision, so nearby objects can be seen clearly. Nearsightedness can usually be corrected with prescription lenses that bend light rays to focus on the retina of the longer eyeball. The opposite problem occurs in a vision defect called farsightedness or hyperopia. A farsighted eyeball is shorter than normal. With this defect, far vision is not impaired, so distant objects can be seen clearly. Light rays from nearby objects, however, are focused behind the surface of the retina. This means close objects are blurry and out of focus. Farsightedness can usually be corrected with prescription lenses that focus light rays on the retina of the shorter eyeball. Astigmatism occurs when there are irregularities in the cornea. This prevents light rays from coming together at the same point on the retina. This can cause blurry images for both near and far objects. Astigmatism can usually be corrected with prescription lenses. Let's take a moment to consider color vision. We see colors because human eyes have 3 different types of cones. Each type of cone is most sensitive to light of a particular wavelength. The different cones are sometimes referred to as S, M, and L cones to indicate whether they are most sensitive to light of short wavelengths, 419 nanometers, medium wavelengths, 531 nanometers, or long wavelengths, 559 nanometers. The colors in the slide indicate how light of these wavelengths appears to someone with normal color vision. A person with normal color vision sees 3 colors in the bar on the slide: green at top, yellow in the middle, and magenta on bottom. In the vase, a person with normal color vision sees green foliage and 2 colors of flowers, red and violet. Color blindness occurs when there is a deficiency in one or more types of cones. One form of deficiency is known as red-green color blindness. A person with this defect would see a solid green bar. In the vase, the person would see green foliage and flowers that are green and pale blue. Let's take a moment to consider how light intensity affects our vision. Our eyes adapt in a variety of ways to see in differing levels of light. One way the eyes adapt is by changing the size of the pupil. In intensely bright light, the pupils are constricted to limit the amount of light entering the eye. In dim light, the pupils are dilated or enlarged to let in as much of the available light as possible. Another way our eyes adjust to dim light is through a process called dark adaptation. After being exposed to bright light, the rods and cones lose some of their sensitivity. When the eyes are in the dark, the rods and cones regain their sensitivity over time. After about 30 to 40 minutes in the dark, our eyes achieve full sensitivity and we say the eyes are dark adapted. To explore the experience of dark adaptation, go outside on a dark night and look up at the stars. Immediately after leaving a brightly lit room, you won't see many stars in the night sky. If you are in a dark location and shield your eyes from bright light, the sky will come alive with stars as your eyes adapt over the next 30 to 40 minutes. You can also see the effects of dark adaptation at night by looking at ordinary objects, such as trees. When you first leave a bright environment, ordinary objects will be hard to see in the dark. After your eyes have had 30 to 40 minutes to adapt, you'll see many objects and details that were not visible before. You may also notice that in the dark, you see mainly in black, white, and shades of gray, even after your eyes are fully adapted. This is because the rods are much more sensitive in dim light than are the cones. Since cones are needed for color vision, we don't see much color in the dark. Let's examine how the distribution of photoreceptors on the retina affects our visual acuity in bright and dim lighting. The macula is a small area in the center of the retina where many photoreceptors are jammed together. In the macula, almost all of the photoreceptors are cones. The macula contains a small pit called the fovea, and the cones are even more densely packed here. In contrast, peripheral areas of the retina are less crowded with photoreceptors, and most of those are rods. During the day and in good artificial lighting, there's plenty of light for the cones to work properly. At this time, objects appear clearest when we look directly at them, so the image falls on the macula and especially the fovea, which again are densely packed with cones. During the day, objects we see out of the corner of our eye are less clear. This is because their images fall on the periphery of the retina, where photoreceptors are relatively sparse. In the dark, when cones are impaired by dim light, we may be able to detect faint objects better when we do not look directly at them, but instead look with averted vision so the image falls on the peripheral retina. You can test this by looking at a dim star at night. A star that appears dim when you look directly at it will appear brighter when you look slightly away. Let's review. Visual acuity is a measure of our ability to resolve fine details or see clearly. Photoreceptors are most densely packed in the macula and especially the fovea. Because of this, we see more detail in good lighting when we look directly at an object so that its image strikes the center of our visual field. The lens changes shape to help us focus on objects at various distances. When focusing on far-off objects, the lens is flattened out. When focusing nearby, the lens accommodates and becomes thicker to bend the light rays more. Nearsightedness, also called myopia, is a common defect in which the eyeball is too long. Distant objects appear blurry because their images are focused in front of the retina rather than on the retina's surface. In contrast, nearby objects can be seen clearly. Farsightedness, or hyperopia, is a vision defect in which the eyeball is too short. Nearby objects appear blurry because their images are focused behind the retina. Far-off objects can still be seen clearly. Astigmatism is a vision defect caused by irregularities in the cornea. Astigmatism can result in blurry images for both near and far objects. Most of us see a broad range of colors in our world. We see colors because human eyes have 3 different types of cones that are most sensitive to differing wavelengths of light. Someone with normal color vision sees 3 very different colors in the bar and 3 different colors in the bouquet. Color blindness occurs when a person has a deficiency in one or more type of cone. One form of deficiency is red-green color blindness. A person with this defect would see a solid green bar and only 2 different colors in the bouquet. In dim lighting, the eyes adjust in part by dilating the pupil opening to let in more light. The eyes further adjust to dim light through a process called dark adaptation. In darkness, the photoreceptors gradually become more sensitive to light. This is a process that can take 30 to 40 minutes to complete. The structures of the eye function to help us see clearly under a variety of environmental conditions. In future videos, we'll examine workplace hazards that can damage the eyes and interfere with clear vision.